big class of the parameter. And that's what I want to tell you. In thermodynamics, and consequently in stat physics, the parameters or quantities are divided to two: intensive and extensive parameters. Some of the parameters are changing by the size of the system, like volume. Huh? Volume is changing. If you make the system bigger, the volume increases. Area also. So they are volume, area, even the size, L. They are increasing by increasing the size. This size. Also, one thing is also this is a simple quantity actually. Not all just this geometrical quantity. The other quantities also, they are intensive actually, extensive parameter. An intensive parameter like pressure. Pressure for the system like a tank of the fluid is independent from the size. It's just as the definition of the force over the small area of that. So pressure is intensive, so it's independent from increasing the size.
Doctor,
yes.
If we increase the size, the pressure will decrease if we keep the force the same, and if we decrease it's going to be obvious, so it's going to change.
It doesn't change, yeah, that's what I say exactly is that. If this is a tank of the fluid, so pressure is defined for each element of that. So you need to consider the F for that and the delta A for that. And the pressure remain the same for all the points. If the system is in equilibrium. If the system becomes in the turbulence or something other thing, like you open a gate here and allow the flow to go, or if you added the flow to that, that will be break the law of the equilibrium actually, all of that. Or if you make hitting the tank, that's a very different process. If the system is equilibrium, if you wanted to keep it in the equilibrium, the pressure for each point will be defined by the same equation. So pressure here will be the same as the pressure here, will be the same as the pressure here. So pressure will be independent from the increasing the tank also the size. And also the force, even the force. So PT, they are a good example of the independent from the increasing the size. I want you to tell you that if you have an intensive parameter like the pressure, forget about the minus or plus. You can put it that. And if you multiply to that change of the extensive parameter like pressure, that will be always give you a delta of some extensive parameter. Like energy here, huh? Like the work, anything. Delta W is P delta V. Extensive parameter, extensive, and this is the intensive parameter. And same like that, you can write it for delta Q. Delta Q is T delta S. Huh? So S is extensive parameter, and T is intensive. Doesn't change by the size. So T is just average of the kinetic energy. So it's really independent from the size of the system. It's really independent from the size of the system, but delta Q will be given as that. So each expression, each differential expression in thermodynamics should be written in terms of the one extensive and one intensive part. So by that you can make it a table for yourself, and you can write it the possibility which you can have to write the thermodynamical equations. So that's a part of the lecture which I needed to check the paper, because I don't recognize some of the thermodynamical equations. For example, energy is normally given as a function of the entropy and the volume, and can be n also, but the number. But just simple case, you fix the number of the n, so energy can be function of entropy and the volume. So if you make a derivative of this equation, delta E will be rho derivative of this delta S plus V delta V. Yes, very generally. So this is not about any type of the cast. Generally speaking, the total energy can be function of entropy and V. We will see that. We will see that for the ideal gas. So just to consider that, and you can compare this equation with this equation, no? From the first law of thermodynamics. So from here you get some simple equation like T is on the E on the S, and the P is minus. Partial derivative in thermodynamics are very problematic, so we need to be very careful about those derivatives. Normally we have it E as a function of S or V, and you get this delta E, huh? Okay? So look at that, if this is correct, so can I write S as a function of E and V? Implicitly you can solve the equation and find S as a function. And take a derivative from that. I want to show you that some step to get a new equations just from some unknown expressions, arbitrary expressions. Partial derivative of this, partial derivative of this. Okay. Can I replace delta E from here to here? So I replace this delta E here. So the S will be okay. Look at that. It's very nice. 1 minus partial derivative of E, partial derivative of this, ds, is equal to you know that the S and the V are considered as independent parameters, huh?
Yes.
So there is no any way to relate the differential to each other. I mean, the coefficient of delta S and delta V should be 0. Otherwise, they will be related to each other. So one will be, it seems very trivial, huh? It seems very trivial, but don't think that this is like remove the delta E by delta E. No. Well, this means that you keep it the volume fixed, and this is keep. What does it mean? This means also to keeping the volume fixed. So from here you get a nice equation. The nice equation is partial derivative of this with respect to S will be 1 over partial derivative of S with respect to the E if you keep it the volume uniform. So immediately, if you compare that with the equation A, if I compare that by plugging to the equation A or using the equation A, what you get? Instead of the partial derivative E with respect to S, I substitute 1 over that. So 1, that will be 1 over T. Yeah. And the other one is very interesting, this equation. Again, the coefficient should be 0. The coefficient here should be 0. So partial derivative of S with respect to this, E with respect to this, minus. Okay. What is the definition of the pressure? Equation B. Pressure is minus 2 on the E on the V when S is constant. Can I replace partial derivative of E with respect to V from this equation? So it will be minus partial derivative of S with respect to V over what is partial derivative of S with respect to E when V is fixed? Is 1 over T. Huh? So T goes. And you can get some equation like that. You see, from the S, from the V, energy is fixed is P over T. And do more calculations like that. For example, you can do like that and you can find the so even one more time, you can consider V as a function of S and E, and again find some new equation. But normally, I just remember these equations that are important. The partial derivative of S with respect to E gives me T if volume is constant, and the partial derivative of S with respect to E will give me P over T. Is energy is a constant. So basically, both using these two equations, I can get any information which I needed. So, and if in your study, if you have n, so if the energy is the function of not only, this is all thermodynamics. You see, we don't use it any statistical physics so far. If energy not only a function of SV but also function of n, so you needed to take the total derivative of this. V and n plus partial derivative of this S and n, S and V, that will be like that. That's these two terms, this is related to the T, and that is minus P from the first law of thermodynamics. And this is, what does it mean? Partial derivative of the energy with respect to the n when S and V is fixed. This is the gradient of energy in n direction. I mean, by changing the number of the particle, I want to know that how much the energy is changing. So this is the gradient of the energy in the n direction if you consider n as a one extra dimension to your physical system, for example. This is a quantity like the pressure, what is called a chemical potential. So chemical potential is given as the inverse of the energy with respect to the n. So this is the there are very different thermodynamical functions like enthalpy, like the Gibbs energy, like free Helmholtz energy. So they are actually related to the our basic parameters, like the total energy, like the pressure and the volume. So we don't use that. So later we will define this. So there are different things like Gibbs energy, G. There is a free Helmholtz energy, F. There is enthalpy, H. For example, F is H is E H is E plus PV, for example. You can find it that in any thermodynamic equations, but we normally just our approach is a statistical mechanics. For me, it's important first to get the function for the Helmholtz energy at least. After that, by Helmholtz energy, I can derive for you all of them. So energy can be related to the F. So PV is related to the F also. So Helmholtz energy is considered as the important things for us. So we are going to find that. So now I'm going to talk about the functional form of entropy or entropy. We talked about the accessible state. I told you that this is the number of the all possibility which you have in your system. Normally, it is related to the number of the energy levels. Entropy needs equations. Actually, we need an evolution equation for the entropy versus the number of the energy level. Even the energy level, number of the energy level is unknown still. So we don't know what is the form of that in terms of the parameter like E, E, V, and so that's also, this is the out part, so this is the out part. It needs to count all possibility. In a quantum mechanical system, with a large number of the accessible states.